Okay, so now let's see how rotations work with energy. So rotational kinetic energy, here we go. All right, so if I apply a force to an object of mass m and that force acts across a distance d, remember it's going to do work. And if that work is done in the direction of the object's motion, it's going to cause an increase in the object's kinetic energy. It's going to go fast, it's going to gain velocity. So the work energy theorem told us that force times distance, work, is equal to a change in kinetic energy. Since it started from rest, it equals 1 half mv squared. But what if I did the same thing, except instead of this object of mass m being a block I'm pushing across a frictionless surface, what if it was like a disk of mass m that was fixed to a wall at a center point and on a frictionless swivel? And I applied the same force F across the same distance d, but instead I just moved it around in a circle like this. This object would be set into a spinning motion, but it would I've done work. It has energy. It has kinetic energy. So that work, that force times distance is equal to the rotational kinetic energy. And to do the kinetic energy, I just go look, instead of m, I have I, instead of v, I have omega. And there you go. It's going to the force times distance is going to equal 1 half I omega squared. So translational kinetic energy and rotational kinetic energy, they're identical to each other. It's just which way the particles are moving. And since it's work done and it's energy transferred, it's going to be measured in joules, just like it was before. So let's just try an example of one like this. We're just going to calculate this and work with it a little bit. Okay, so let's just say I have a 6 kilogram disc, solid disc, radius of 0.25 meters, and it's rotating in a clockwise direction at 16 radians per second. So normally we say that's the negative because of the right-hand rule, but it doesn't matter because we're talking about energy. So the rotational kinetic energy is equal to 1 half I omega squared. In this case, it's a solid disk. You don't have to memorize this, but you'll be told this, but you do need to be able to work with it. That for a solid disk, I is 1 half mr squared. So therefore, I'm going to expand to this. I'm just going to substitute in the values. For mass, I'm going to put in 6. For radius, I'm going to put in 2.5. For omega, I'm putting in 16. And I come with 24 joules. So it has 24 joules by virtue of doing this. But what if this object wasn't just sitting there spinning on like a fixed point on the wall, but is rolling across the floor? If it's rolling across the floor, in addition to having rotational kinetic energy, it also has translational kinetic energy. Okay. And so in this case, I'd had to take both into account. So its total kinetic energy is both its rotational kinetic energy and its translational kinetic energy. So we saw from before when we calculated rotational kinetic energy, it'd be 24 joules of rotational kinetic energy. Now I want to know what its translational kinetic energy is, 1 half mv squared. But before I can do 1 half mv squared, I got to know what v is. So that's why we have to memorize that alpha times r equals x, omega times r equals v, I'm sorry, I'd say theta times r equals x, omega times r equals v, and alpha times r equals a. So in this case, omega times r equals v. So therefore, v is 4 meters per second. I can then calculate the kinetic energy of translational energy by saying 1 half mv squared. The mass is 6. The translational velocity is 4. That gives me 48 joules. So the total kinetic energy is 48 joules of translational plus 24 joules. And notice that's half. And that gives me a total of 72 joules of, of total kinetic energy. Now, remember, positive a force that acts in the direction of motion does positive work can cause the kinetic energy to increase. Well, let's say this can be true for rotation. So a torque that acts in the direction of rotation is going to do positive work and cause the rotational kinetic energy to increase. And a torque that acts in the opposite direction of the rotation does negative work and causes the rotational kinetic energy to decrease. Let's take a look at a system like this. I've got two 2 kilogram masses, 1 meter apart, connected to each other by a rod of negligible mass. And the center of this is connected to a spool of unknown radius around which I wound very tightly 3 meters of string. And I'm going to pull on this string with a constant force of 10 newtons. So what I want to know is, what is the final angular speed of the system? Well, I can't just use kinematics because I don't know what, or I can't use forces because I don't know what this radius is, so I don't know what the torque is, but I do know that the work being done is going to be equal to the force times the distance, so I can solve this. Let's do it. So I'm going to use the work energy theorem to solve this. I'm going to say, well, the work done is going to equal the change in the rotational kinetic energy, and it started off at 0. So therefore, force times distance is going to equal 1 half I omega squared. Now, in this case, the system has a total rotational inertia of mr squared plus mr squared. I have two objects that are a distance r away. So now I can just substitute in these values. I can say, well, force is 10. I apply 10 newtons of force across 3 meters of string. The mass, I can say, well, 1/2 of, I have 2 kilograms, and now the radius is half, remember, because the axis of rotation was halfway across that 1 meter, so 0.5 square, and I have two of those. And so then I just, now everything's substituted in, I just solve it, and I get 7.75 radians per second equals my omega value. But that's how I would use this work energy theorem in the sense of a rotating object. Let's talk about conservation of energy. So conservation laws are very powerful. They're the most powerful tools we have in our physics toolbox at this point because they let us solve a lot of seemingly complex problems. They let us simplify these problems. So basically, we're just going to add, instead of just saying mechanical energy is equal to gravitational plus kinetic, or just potential plus kinetic, we're going to take springs out of this. We're going to add kinetic, meaning translational kinetic, plus rotational kinetic. So we're just going to add this into our already existing energy equation, and otherwise it's just the same. So here's a classic problem. You will see something just like this on the test. I have, in this case, I think a sphere. I have a solid sphere, just to mix things up a little bit, instead of a disk of unknown mass and radius. It rolls without slipping. Now, when you see these words without slipping, let's just talk for a minute about what that means. That means that the static frictional force, which doesn't move, right? So it doesn't do any work, but it does apply a torque. So that static frictional force is, the object is trying to move this way, so the frictional force is that way. So it's applying a torque, which is going to cause this thing to rotate this way. If that wasn't there, if this was a frictionless surface, there would be no torque. This thing wouldn't rotate, and it would just come to the bottom with only translational kinetic energy. So when we see that word without slipping, it tells us you have to take into account rotations. If it says it's frictionless, then there's no rotation. It's just going to come to the bottom. There's no torque, or there's no static force to push it into that direction. Okay, so now we're going to apply energy conservation, like we said before. The thing to keep in mind is it started from rest, so it didn't have any translational kinetic energy, it didn't have any rotational kinetic energy. All it had was gravitational potential energy. At the bottom, it doesn't have any gravitational potential energy, but it does have both translational kinetic energy and rotational kinetic energy. So I'm just going to take these and substitute in what they are. So I have mgh for my gravitational potential energy. I have 1/2 mv squared, like I've always had before, for translational kinetic energy. And now I'm going to add in, I have 1/2 I omega squared is my rotational kinetic energy. Now, you don't have to memorize this, but a sphere has a certain I value that would be given to you on the test. You don't have to memorize these, but for a solid sphere, it's 2/5 mr squared. So I'm simply going to substitute that in for I, and I'm going to use that standard trick we've been using, where I'm going to take omega and I'm going to replace it with, since omega times r equals v, then uh, then then that means that omega is v over r. So I'm going to substitute that in, square it. I end up getting rid of my m's, I get rid of my r's, I get this, and I get my v value is the square root of 10/7 gh, which, by the way, is less than what it would be if it was frictionless, because if it was frictionless, it wouldn't rotate. I'd only have translational kinetic energy, and I think you probably remember from before, hopefully, that when I have this problem here, I end up getting root 2 gh is what I get when an object falls a certain height, and it's just gaining translational kinetic energy. And you'll notice this value here, root 2, is significantly larger than root 10/7. So the difference is that it's got rotational kinetic energy when it goes to the bottom. All right, let's try this one here. So now I've got an object of mass m is going to fall a distance h, and it's connected to a disk of mass 4m and radius r. And what I want to know is how fast will this object be going when it reaches the ground, after it's fallen height h. Now, if I just cut it, it'd be going root 2 gh, but it's going to be doing something different here. So I'm going to do conservation of energy. Again, I'm starting off with no kinetic energy. I just have UG. I'm ending up without any UG, so I just have kinetic plus K rotational. So this is basically all we've changed. Is we've just taken and we've added this to it. Like we did before, mgh equals 1/2 mv squared plus 1/2 I omega squared. Again, I'm going to substitute in for omega. So for omega, for I rather, in this case, it's a 4m object and it's a disk. Now remember, for solid disk, it's 1/2 mr squared, so 1/2 4mr squared, because its mass is 4. And again, I'm going to take omega and make it v over r. And then what happens is I get rid of all my m's, I get rid of all my r's, and I'm left with this. And then I solve for v, and I get its root 2/3 gh. Last one, I promise you. Okay. So we often don't think about this, but a car has wheels, and wheels have mass, and we can treat them like a hoop. And in a hoop, this is the eye of a hoop is just mr squared, right? But really, I have four of these hoops attached to the car. They have mass, so they do have rotational kinetic energy that we usually ignore, but now we're not going to. So what we're going to say is, I have a car has a mass of 20 traveling at speed v. The light turns red in front of it. It's got to slow down and stop. So I have to do negative work. Well, so I have to get rid of all my kinetic energy in order to come to a stop. So now I'm not just considering the mass, the kinetic energy of the car, but I'm also considering the rotational kinetic energy of the wheels. So what I want to know here is, what percentage of the total work done is attributable to the work needed to account for the rotational kinetic energy of the tires. Really, we're just saying, what percentage of the overall energy of this moving object is in its tires. So I'm going to say, well, work equals kinetic energy plus kinetic rotational energy, right? That's how much work I do to bring this to a stop. And remember, for a hoop, the I value for a hoop is just mr squared. Really easy. So, but the one that came minus, I have four tires. So I have 4 times 1/2. So basically, each of these has kinetic energy, right? So I have a car which has kinetic energy, plus I have 4 tires that have kinetic energy, and they have rotational kinetic energy, which is I omega squared. Now I'm just going to substitute in the known values. Well, so the value of the car itself is 20 m, and the tires are just m. So I have 4 times 1/2 mr squared. And again, I'm going to take omega and turn it into v over r. And so my m's go away, my r's go away, and I didn't get. No, I can't get rid of my m's because I have a w over here. But I get rid of my r's, and I end up with 10 mv squared plus 2 mv squared. So this is the car, this is the tires. So I have a total work done is 12 mv squared. Now, of that 12 mv squared, 2 of it was the tires. So that means 16.7%, or 16 and 2/3 of the energy that was expended was in order to account for the rotation of the tires. Hey, thanks for watching. I know I went kind of quick, but I screwed this up so many times. I'm just ready to go home. It's 5 o'clock on a Friday, and I am done. Okay. Hey guys, we're almost done with our physics year. Thanks for watching.